Hi everyone, welcome to Calc Lesson number 51. Today we are going to continue talking about area under the curve. We are going to use the summation notation that we reviewed in our last lesson to actually start talking about area under the curve and specifically the limit definition of area under the curve. Here we go. Okay, so before we jump into the handout for today, we want to do a quick warm-up to review the summation formulas and properties that we were reviewing in our last class. So to warm up here, we want to evaluate the sum from when I equals 1 until n of I plus 1 over n squared. And we're going to evaluate that for several values of n, starting with 10, then 100, 1,000, 10,000, and we'll start to see what happens as n gets really, really large. So if we're thinking about this summation, we have this sum from when I equals 1 to n of I plus 1 over n squared. Now, in the past couple that we were doing last time, we always had an n value that was a number. So we had numbers like 6 or 10 or 20. In this case, we just have n. So our goal here is going to be to write this not as one number, but as a formula for when you can just plug in n2. So we want to rewrite this completely in terms of n. Also notice that we can't quite jump in with a formula yet. We have to first use the properties to manipulate this summation before we can use the summation formulas we were given. So the first thing I want to notice is that I have an n squared in my summation, and n is my upper bound and is representing some kind of number, 10, 100, 1,000. So that's going to be a constant. So we can use the first property where we can actually pull our constant out to the front. So let's write this as 1 over n squared times the sum from when I equals 1 to n of I plus 1. I'm just going to use parentheses to make sure that that's clear. From there, we can use the second property to actually split up that summation into the summation for I and the summation for 1. So let's write this as 1 over n squared times, and then let's split this as the sum from when I equals 1 to n of I plus the sum from when I equals 1 to n of 1. So those first couple of steps are just using the properties that were given to you in the last class. Now, if you have the summation formulas readily available, I would definitely grab them as they're going to be helpful to us. As a quick reminder, the sum from when I equals 1 to n of any constant c is just equal to Cn, and the sum from when I equals 1 to n of I is equal to n times n plus 1 all over 2. So if you don't have your handy formula sheet, that's okay. These are the two formulas we're going to be needing for right now. So let's continue simplifying this. So we keep our 1 over n squared on the outside. Our first term, the sum from when I equals 1 to n of I, looks just like this formula. Because our n value is just going to stay n, we can actually replace it entirely with this formula, n times n plus 1 over 2. Plus, for our second term, we have the sum from 1 to n of 1, and 1 is just a constant. So this summation is equal to 1 times n, or just n. So we've used those formulas to write this summation completely in terms of n. Now we want to simplify before we go ahead and plug in. So let's write this as 1 over n squared times n squared plus n over 2 plus, and I'm going to change this n to be 2n over 2. So I think it'll make it a little bit easier for me to simplify. So this becomes 1 over n squared times n squared plus 3n over 2. So we're looking to simplify here. Let's take an n out of our numerator. So we have n times n plus 3 over n times 2n. Just breaking up that n squared so that I can see my n's are going to cancel. So we have simplified this summation down to n plus 3 over 2n. Now remember, that's not the end. We actually want to evaluate when n is 10, 100, 1,000, 10,000, and so on. So I'm going to set up a little table. And I'm going to reach for my calculator, and for each of these, I'm plugging in to my new formula. So if I plug in 10 in for n, I have 10 plus 3 over 2 times 10, and I should get a decimal. Go ahead and do it on your own and then come back and check. Filling in this table, you should get 0.65 for 10. Plugging 100 into that formula, you should get 0.515. Plugging in 1,000, you should get 0.5015. Plugging in 10,000, we should get 0.5002. And now we want to make some kind of guess or estimate about what's happening as n is getting really, really big. So hopefully what you're noticing is that as our numbers were getting bigger, our value was getting closer and closer and closer to that 0.5, that exact value of 1/2. So as this n value was going towards infinity, this summation was going to 0.5 or 1/2. So if you guys remember from way back, the last time we were looking at tables like these, when we were talking about limits. So we can say the limit as n goes to infinity of this value, n plus 3 over 2n, is equal to that exact value of 1/2. So a quick warm-up, that's kind of the concept we're going to be using today to kind of combine all of our knowledge about summations and limits and talk about area under the curve. So pause the video if you have any questions, ask your teacher. Otherwise, we're going to get started with that handout. All right, so as we get started with this lesson, we want to recall a function that we were working with just last week, and that function is f of x equals 2x plus 1. So we wanted to draw 4 equal width rectangles over the interval from 0 to 2, and we've reviewed how you can do that in a couple different ways. So on the left, we used the upper left endpoints of our rectangles on the function. So we defined the height by our function on the left endpoints at f of 0, f of 0.5, f of 1, f of 1.5. And the area that we found using these rectangles was there. And then on the right, we use the upper right endpoint of each function. So we use the heights as f of 0.5, f of 1, f of 1.5, and f of 2. And then the area we calculated with these rectangles was included in all of this shaded region. So hopefully you guys remember doing a couple of different examples using this function 2x plus 1. So in those examples last week, what we did was actually add up the 4 rectangles to find a summation, which actually can be written out using sigma notation. So to write using sigma notation, us adding all of these rectangles, we would use the sum from when I equals 1 to 4, because we have 4 rectangles, of the width times the length. So the width, remember, is going to be the distance between each rectangle, or the interval of each rectangle. So that's our 1/2. And then the length, or the height, would be represented by what is plugged into the function. So that's where it's going to be different. So our width is the same, but it's going to be different for whether we are using our right endpoints or our left endpoints. So if we're using our right endpoints, then we need to account for 1/2 I. So if we have 4 rectangles, 1 through 4, we're starting at 1, then our endpoints happen at f of 1/2 of 1, which is 0.5, 1/2 of 2, which is 1, 1/2 of 3, which is 1.5, and 1/2 of 4, which is 2. And then on the left, it's 1/2 of I minus 1. So if we starting at 1, 1 minus 1 gives us 0, and 1/2 of 0 is just 0. Then we go to 2, 2 minus 1 is 1, and 1/2 of 1 is 1/2 or 0.5. 3 minus 1 is 2, and 1/2 of 2 is 1. And then 4 minus 1 is 3, and 1/2 is 1.5. So the difference there, the biggest difference in these formulas, is in calculating what you're plugging in to find your length. So in a second, we're going to go through these limit definitions and show how they are the same. So as you guys noticed through our several explorations last week, the more rectangles that we divided the closed up interval up into, the closer our approximation for the area will be. However, it doesn't make sense to continue finding the area of each rectangle and then adding them up. So instead, we're going to use limits of the lower and upper sums where the numbers of rectangles approach infinity. So then here you have these two definitions. Now in the last slide, or in the up above on your handout, we looked at the specific limit definitions for the function 2x plus 1, the 4 rectangles that we had drawn. Here you have your generic or your formulas for your limit definitions. So you have the limit as n goes to infinity of the sum from when I equals 1 to n of b minus a over n, where b is your right bound and a is your left bound, and then n is your number of rectangles, times the function evaluated at b minus a over n times I for your right, and then the same thing but times I minus 1 for your left. And remember, what you're really finding is the limit as n goes to infinity of the sum of all of your rectangles, where you're just doing your width times your length, where your width is the equal intervals of your rectangles, and then your length is evaluated by the height of the function plugging into your function f. So this limit is finding out what the value would be if you took as close to infinitely many rectangles as you could. Okay, so we're going to go through the limit definition for the example on your page. So we are looking to find the area on the interval from 0 to 2 for your function f of x equals 2x plus 1. And we're going to start by going through the limit definition for the right endpoint. So from above on your handout or the last slide, this limit definition is the limit as n goes to infinity of the sum from when I equals 1 to n of b minus a over n times f of b minus a over n I. So as you can see, this is already worked out for you on your page. We are going to talk through this one, make sure we all understand it, and then we'll go through a couple of examples. So here we have the limit as n goes to infinity, so in our first line, of the sum of n equals, from the sum from I equals 1 to n, and then filled in for us, we have the 2 minus 0 over n and the 2 minus 0 over n. So we are just getting those values because our a equals 0 and our b equals 2. So we are using our endpoints there, plugging them in for a and b. Into our next line, we are just going to simplify and get rid of those zeros. So this becomes the limit as n goes to infinity of the sum from I equals 1 to n of 2 over n times f of 2 over n times I. Now from here, we are going to do what we did in the warm-up, where we want to take any piece that has that I in it and eventually expand it out until we just write it in terms of n. So we want to write our sigma in terms of n. That is our goal. So in order to do that, we want to take this notation, this f of 2 over n times I, and we actually want to plug it in to get rid of that f of x notation. So knowing that our function f of x is equal to 2x plus 1, we're actually going to plug in 2 over ni for that x. So that's how we jump down to this next line. We are just plugging that in to our function f. So we have this whole beginning part stays the same. The limit as n goes to infinity, the sum of I equals 1 to n of 2 over n, and all we changed in this line here is we plugged in to our function. And now we are just going to simplify. So we multiply 2 times 2 gives us 4 over n times I plus 1. And then in our next step, so in this last step, we kept this beginning part again. In our next step, we're actually going to distribute the 2 over n to both terms. So now we have in this line here the limit as n goes to infinity of the sum from when I equals 1 to n of 8 over n squared I plus 2 over n. Now in this next line, we are going to use, let's use a better color, we are going to use the properties just like we did in the warm-up. So we're going to leave our limit on the outside, but we're going to take our summation and we're going to split our summation. And we're going to bring our constants out front. So this 8 over n squared is just a constant, so it goes out front. 2 over n, also just a constant, it goes out front. We can leave our I, and when you pull the 2 over n out, you are just left with a 1. So take a second, and if you don't see that step, because there's a lot happening, ask your teacher to pause the video and to kind of go over how you got there. From there, this is where you want to keep those formulas handy so you can go ahead and reference them. So you want to recognize that you have the sum from when I equals 1 to n of I. Your formula is equal to n times n plus 1 over 2. And the sum from when I equals 1 to n of c is just equal to cn. Those are your formulas from the other day. So you can actually replace your summations with those formulas. And in this case, just like in the warm-up, c is equal to 1, so it's just equal to 1n. And then again, keep your constants that you pulled out, 8 over n squared and 2 over n. From there, you want to go ahead and actually simplify. So you're going to combine this whole parentheses. You have 8 over n squared times n plus 1 over 2 plus 2 over n times n. So notice your n's cancel, so you're just left with a 2. And your first term turns into that 4 plus 4 over n. And then finally, just combine your 4 and your 2. So you are just left to evaluate the limit, the limit as n goes to infinity of 6 plus 4 over n. So now we have to think way back to the beginning of the year talking about limits. The limit as n goes to infinity, you would have 6 plus 4 over infinity. Remember, anything divided by infinity is going to be equal to 0, so you are left with 6 plus 0 just equals 6. So this limit, all the way at the top here, as n goes to infinity, of the sum from when I equals 1 to n of these rectangles, right, we're finding as many rectangles as we can, is just equal to 6. So pause the video if you need to, ask any questions, and we're going to quickly look at the left endpoint and see how those are similar. Now, we just went through the whole right endpoint in detail. We're not going to go through this all in detail. If you are interested in going through it, I'm sure your teacher would be happy to go through each piece with you. But just looking at the steps, hopefully you recognize very similar steps here, the only difference being in this how you are finding the height of each rectangle. Otherwise, you are still finding the limit and the sum, and you're following the formula. And if you look all the way down, you still get an answer of 6 in this case. So since the limits are the same, it actually doesn't matter which endpoint you choose. Okay, so reading through one is always fun, but I think it'll be best if we just go ahead and actually do one together. So we're going to go through 2 examples, and then you guys are going to have 2 examples to try on your own tonight for homework. So for number 1, we want to find the area by the limit definition of the region bounded by the graph f of x equals 9 minus x, the x-axis always, and vertical lines x equals 0 and x equals 4. So those vertical lines are actually giving us our a and b, so they're telling us that a equals 0 and b equals 4, and that's going to only really be helpful if we know where to plug them in. So the limit definition that we're going to be using here is the limit as n goes to infinity of the sum from when I equals 1 to n. And then remember to find our width, we would have b minus a over n times our length or our height. So this would be f of, and then remember the difference would be if you're choosing left or right, just like we saw in the last 2, or in the little exploration. It doesn't matter what you choose, so I'm going to choose the easier one and just do b minus a over n times I. So this is our limit definition of the area under the curve. Just like we did in the sample, I'm going to start by just plugging in my b minus a. So I'm going to keep my limit as n goes to infinity of the sum from when I equals 1 to n. And I'm just going to plug in my 4 minus 0 over n times f of 4 minus 0 over n times I. And then we know that 4 minus 0 really just simplifies to 4, so I'm going to keep on writing this step, but if you guys just want to skip ahead and not write this 4 minus 0 part, that's fine too. So we have the limit as n goes to infinity of the sum from when I equals 1 to n of 4 over n times f of 4 over n I. So we've plugged in our a and our b. From here, our next step is actually to take this f of 4 over ni and plug it into whatever our function f of x is. So we're going to plug a 4 over ni in for this x. So we have the limit as n goes to infinity of the sum from when I equals 1 to n of 4 over n times, and then this would be 9 minus 4 over ni. Now, before we can split apart this sum, let's go ahead and simplify. So let's distribute our 4 over n through. So we have the limit as n goes to infinity of the sum from when I equals 1 to n. 4 times 9 is 36 over n, minus 4 times 4 is 16i over n squared. So now that we have the summation completely in terms, or we've simplified our summation, we got rid of the f notation, we can go ahead and split it up using the summation properties. So I'm going to bring this up to the top. I'm going to keep my limit as n goes to infinity on the outside, and I'm going to use some large brackets. I'm going to split up my summation and pull my constants out to the front. So the constant in my first summation term, 36 over n, I can pull to the front and write this, as 36 over n times the sum from when I equals 1 to n. Because there's nothing left, there's like an invisible 1 here, so times 1, minus, for my second term, my constant is at 16 over n squared, so I can pull that out, times the sum from when I equals 1 to n, and what's left over is I. Once you split it up, now you can locate your 2 summation formulas and then actually use the formulas from your previous lessons to plug them in. So keeping our limit as n goes to infinity we have 36 over n times when you plug in a 1, or I'm sorry, when you follow this formula, 1 times n is just n, minus 16 over n squared, and then following your formula, this is n times n plus 1 all over 2. And then from here, we just want to simplify this down so it's nice and clean for us to take our limit. So let's keep our limit as n goes to infinity. Now we can cancel out these n's, and we can cancel this n with one of these n's, and this 2 and 16 just becomes an 8, so this makes it a little bit easier. So we have 36 minus, and this becomes 8 over, or let's see, distributing our 8, we get 8n plus 8 over n. So if we write this as the limit, as n goes to infinity, this would stay 36, minus, if we split up this fraction, 8n over n just turns into 8 plus 8 over n. So when we actually go to take that limit, actually let's first simplify this 36 minus 8, so we're taking the limit as n goes to infinity of 36 minus 8 is just 28 plus 8 over n. When you plug in your limit, you have 28 plus 8 over infinity just goes to 0. Oops. Sorry guys, these should all be minuses because I totally didn't distribute my negative. Not that it matters, minus 0. So our limit just goes to 28. So ultimately, a quick recap, what we're doing here is finding the area bounded by the region using the limit definition. And so if we were to use infinitely many rectangles, we would get an area of 28. Okay, just one more example for today. Here we want to find the area by the limit definition of the region bounded by, this time, the graph of f of x equals 3x squared plus 1, the x-axis, and then our vertical lines, x equals 0 and x equals 2. Remember, these are our a and our b values, and that's most helpful if we know what to plug them into. So our limit definition is the limit as n goes to infinity of the sum from when I equals 1 to n of b minus a over n times f of b minus a over n times I. So if we start by just plugging in for b minus a, that's 2 minus 0 in both cases. So we have the limit from when as n goes to infinity of the sum from when I equals 1 to n of 2 minus 0 is just 2 over n times f of 2 over n I. From here, we want to take this out of this function notation and actually apply it in the function. So we can write this as the limit as n goes to infinity of the sum from when I equals 1 to n, keeping our 2 over n times, our function is 3 times 2 over ni squared plus 1. And then we have to actually simplify that, so we have to keep on writing the limit as n goes to infinity of the sum from when I equals 1 to n. Keep our 2 over n, and let's write this as 3 times 4 over n squared I squared plus 1. And then from there, let's actually multiply that 3, so we have the limit as n goes to infinity of the sum from when I equals 1 to n of 2 over n times 12 over n squared I squared plus 1. And then finally, before we can handle our summation, let's just distribute this 2 over n to both terms. So we have the limit as n goes to infinity of the sum from when I equals 1 to n of 24 over n cubed times I squared plus 2 over n. Now that we've rewritten that, we can go ahead and separate our summation. So I'm going to bring this up top here. So let's keep our limit on the outside. And then we can split this and pull those constants out front. So let's pull this 24 over n cubed out front, and the 2 over n, also a constant. So we have 24 over n cubed times the sum from when I equals 1 to n of I squared, plus 2 over n times the sum from when I equals 1 to n, and then since there's nothing there, it's an invisible 1 of 1. Now looking at the two pieces that we have the sum of I squared and the sum of 1. So thinking about the formulas that we might need, the sum from when I equals 1 to n of a constant c is just c times n. And then a new one to use today is the sum from when I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 all over 6. So again, if you have that formula sheet, that's going to be really helpful to continue referencing as you do these problems. So from here, we can actually go ahead and fill them in. So keeping our limit as n goes to infinity, let's keep our 24 over n cubed, and let's replace this I squared with n times n plus 1 times 2n plus 1 all over 6. Plus, let's keep our 2 over n, and then the sum from I equals 1 to n of 1 is just going to be n. Whoops, wrong bracket. So now that we've taken it out of that sigma notation, we can just go ahead and simplify this as best as we can until we can apply our limit. So a couple of things we can cancel right away. I know that 6 goes into 24 4 times, and I see an automatic n I can cancel here, and an automatic n I can cancel here. So this leaves me with the limit as n goes to infinity, and then I have 4 times n plus 1 times 2n plus 1 all over n squared plus 2. And now I'm actually going to have to simplify what's going on inside here. So I have the limit as n goes to infinity, multiplying my 4 into my n plus 1. I get 4n plus 4 times 2n plus 1 all over n squared plus 2. And then I'm actually going to FOIL that out. So I have the limit as n goes to infinity, and then 4n times 2n gives me 8n squared, plus 4n plus 8n gives me a plus 12n, and then 4 times 1 is just 4, all over n squared plus 2. Now because I have more terms in my numerator than my denominator, I'm actually going to split this fraction. So I have the limit as n goes to infinity, splitting this as 8n squared over n squared plus 12n over n squared plus 4 over n squared plus 2. Canceling what I can, n squareds cancel out, 12n cancels with 1n, and then I'm left with that 4. I'm running out of room, but we're almost done. If we bring this up top here, what we're finding is the limit as n goes to infinity of 8 plus 12 over n plus 4 over n squared plus 2, which is really just the limit as n goes to infinity of 8 plus 2 is just 10, plus 12 over n plus 4 over n squared. As we take this limit, our 10 stays, 12 over n goes to infinity, right? Anything goes to 0. Whoops, anything divided by infinity is going to go to 0. 4 over n squared is going to go to 0. So this limit as n goes to infinity is just equal to 10. So take a second, look that over. It's a lot of work, but you are essentially using the limit definition to find the area bounded by the region of your function, your x-axis, and then your two vertical lines. Okay, great job with these. I know that these problems can be tricky, so if you have any questions, please reach out to your teacher for clarification. Homework 51 is going to be just done on a separate sheet. You have just these two problems, so for each you are going to be finding the area by the limit definition, then you have two separate functions and separate bounds, and then just note you can actually check your work for each by finding your definite integral and then evaluating using that fundamental theorem of calculus. So in the homework, you're going to be using the limit definition, but you can for sure check your work by using the fundamental theorem of calculus. Okay, great job, everyone. See you next time.